So in these two talks, I will first finish a kind of abstract part that you can of what you can say about these motivic triangulated categories and the six-functors formalism. And actually, the talk today will be about constructibility and finiteness conditions on objects, and the second talk will be on Wajewski's motivic complex. We have seen them during the week, so I will recall the construction and some known facts. Okay, so far what we have done is that I have shown you some axioms on a fibered category. So if T is so-called motivic triangulated category, then using construction of Wajewski, Ayub, and some complement that we have given with Cieszynski, you get a full formalism of 6 operations. So F upper star, F lower star, P lower shriek, P upper shriek for P separated of finite type, tensor product, and internal OM. So just a word. I have not said a lot about this adjoint last time, but so P upper shriek is right adjoint to P lower shriek, and it exists in practice. It exists formally. Say, for example, from the fact that T is compactly generated, you automatically get this adjoint here. So the example that we have seen so far is T is a stable homotopic category, VA1 category with for topology T Nisnevich and et al. With coefficient in arbitrary ring. And today I will try to give some example and application of what I'm saying. So I will use in advance the category DM or in some good cases. So good cases, which I will review in next talk. There are other categories that you can obtain from this one, and these are obtained from ring spectra. So if, admit you have a Cartesian section, a well-behaved ring spectrum over each is scheme S, which is stable by base change, then you will get, you can consider modules over this ring spectra if it's well structured, and you can consider the associated category. So this applies in particular to KGL. So you can consider KGL module and also MGL module, and so on. All these categories are automatically satisfy all the axioms, and so you can apply the general construction. Okay. So that's already a lot of example, and of course the classical settings of étale sheaves of torsion étale sheaves or L-adic étale sheave on the small site enter into these frameworks, but the fact that it's motivic is non-trivial in that case. Okay. So, as I said, today we will speak about constructibility, and the goal is to introduce good finiteness condition on this category, because in order to get all these operations easily, we have more or less used the fact that T admits infinite sums, for example, to get the model structure and so on. And so now, if we want to formulate some duality result, of course we must forget this condition, because it's well known that you cannot have a dualizable object if you have infinite sums. So the natural condition for as a finiteness condition is that of constructibility, and I will state it now. So we take an abstract category like that, and we assume that we have 6 operations. Then we define subcategory of constructible object. the definition is quite easy, is TC of S, the full triangulated subcategory generated by these objects X over S smooth and Y an integer. So I mean, this means full triangulated thick subcategory generated by these objects of T of S. Okay, so thick means that you add the direct factors, and triangulated subcategory means that this category is stable by extension. Okay, so we forbid the fact that we have infinite sums in this category. So in these cases, this category is can be actually characterized. So say what you need is that if T is what I call Tate compactly generated, which means that these objects are compact and generates the category under infinite direct sums, the category this one under infinite direct sums, then TC of S is equal to a category of compact objects, or maybe we say then M is constructible if and only if M is compact. Okay. So that actually, this finiteness condition looks very much like the condition of being perfect by a result of Thomasson. Being a perfect complex in the category of A module, say, or OX module. Okay. So this assumption appears in all these cases, except in the case where T is the étale topology and we have infinite cohomological dimension for the basis. Okay, so first question is the basic question, say, is TC stable under the 6 operations, so F star, and you write like that, P shriek tensor, F lower star, P upper shriek, and internal on. Okay. So for these two ones here, this is obvious. This is by definition. So I'll tell you that if you recall the formula, these objects, by the way, recall that this is P sharp, P upper star, and for P the projection. Okay, these objects are stable by these operations because these generators acts obviously on these. For this one, you can use dévissage and reduce to P is equal to Y, a closed immersion, or P is smooth. So when P is smooth, we have seen that P lower shriek, in that case, P lower shriek is isomorphic to P lower sharp tensor term space tangent. Yeah, I think it's okay. Maybe it's minus, sorry. And so in particular, P lower shriek respects the constructible object. And for closed immersion, this is just an exercise. You use the localization for the closed immersion I. And so in some part you will have Y lower star of some constructible object, and in the other part you will have J lower sharp, J upper star of the object. So while our star is presented as a cone of constructible object by the localization. So actually, the stability by these operations, which is obvious. So recall that these are left adjoints. And the problem is the stability with respect to these operations. And in particular, you can reduce that to this one. Okay, so in the talk now, I will present first tools to study these questions, and then I'll give you the theorem which solve the problems, and also in the same time how you can deduce duality from this result, and some facts. Okay. So first, I'll present two tools, which are nonetheless useful also for other questions than this one. So the first one is the continuity property. So I need a little bit of notation to formulate this. So the basic problem is to compute cohomology of projective limit of schemes. So let's consider SI, little I in big I, a projective system of schemes. Usually you consider with affine transition morphisms. So that the projective limit of this system of scheme exists as a schemes, and you assume such that, say, the projective limit of the SI belongs, call it S, belongs to our category of base schemes. Maybe I should triangulated category over a suitable category of schemes. S. In the application, S is either the category of all Noetherian finite dimensional schemes, or the schemes over some base like a field or a Dedekind ring. Okay, so here we will in particular assume that, for example, S is Noetherian finite dimensional, which is not automatic, of course. And also we consider that an index Y0 in I and E0 just an object of TS0. Then in that case we can define the cohomology for any, say, phi from X to S, any schemes in S. We can define the cohomology of it0 as, I will write ENI of X as the in T of X of a unit object over X, and you take the pullback phi upper star of E0 twisted I times shifted n times. Okay, so this cohomology theory is contravariant in X easily. S0, sorry. So in particular, if you replace I by I over comma I0, you can assume that the cohomology is defined on all the on the terms of this projective limit of schemes. So the definition is a bit brutal of continuity, what I will take today. one says that T is continuous if any time that the above assumptions hold. And as a formula, the canonical map from the inductive limit of integer I in I over I naught of E star star X going to E star star of, this is Si and this is S. So there is a canonical map like that by contrariant functoriality, and you ask that this is an isomorphism. Okay, so this basically tells you that you can compute cohomology with coefficient, with any coefficient relative to t by of the projective limit here by this thing. This property is of course extensively used by in the theory of étale cohomology by Grothendieck for various things. So I will give examples below. So this definition is a bit rough, but the fact is that all categories in our example above example are continuous. So I don't enter into the details. The basic fact is that the definition of these categories relies on the formalism of sheaves, and if your scheme satisfies good finiteness property, and this is why I need, for example, Noetherian, this could happen if you use, for example, quasi-coherent, quasi-separated schemes if you want, but Noetherian is fine. And so if your scheme satisfies these assumptions, and if you are in some category of sheaves with a reasonable topology, then this property will hold for the cohomology with coefficient in the sheaf. And then because of the procedure, so you can control then the procedure of A1 localization and stabilization and show that this property persists. So we gave a criterion with Cieszynski in our paper for the triangulated category that are homotopy category of model categories, but okay, it's sufficient for us to know that this property is true in these cases here. So what is it used for? Once you have this property on cohomology, then you have a more interesting property. So let's assume that T is continuous. Then we can say it like that. If S is projective limit of some schemes Si, everyone belongs to S. Oops. Then we have an equivalence of category. Then the category of constructible object over S is equivalent by the canonical map like that to the two co-limits of the categories TC of Si. So
you are assuming that this limit also lies in this category S or T?
yeah.
So it may happen that Si are Noetherian but S is not also.
What?
So suppose Si are all Noetherian, it may happen that S is not also.
Yeah, sure, but I require that the projective limit is Noetherian, for example. So this is the point that I wanted to make. You have to assume something on the projective system. In practice, that's what you have. Usually, you'll see we want to use that. For example, you have a schemes and you localize it, and you want to use this property for the localized scheme. So usually the projective systems are quite obvious. Okay, so what does it mean? S? No, which one? This here? This means the... okay.
The calling it is, but before the calling you have
Let's see. There's a canonical equivalence. This? And there's a 2. This is a 2. Yeah, but I will translate this. Usually, this is how people write this. This means the co-limit in the 2 category of categories. But I will explain what it means concretely. So this means 2 things. No. Okay. So first of all, if you are given Mi, Ni, a family of constructible, say, primitives over Si, such that for all transition map phi ij, you have phi ij, a canonical isomorphism, say, phi ij nj is equal to Mi, phi ij nj is equal canonically isomorphic to Ni. Then you have a canonical map from the, let me write inductive limit from the morphism in T, Si, Mi, Ni to the morphism of S of M and N. M is a pullback of any I where phi I is just projection. Okay. Then this is an isomorphism, so you can compute morphism between projective systems of motifs, and also you can lift objects. So if you have M, a constructible object over S, then there exists an index I in I, and an object Mi which is constructible in Si, such that, say, M is isomorphic to phi I upper star of Mi. Okay. So you can compute morphisms and objects lifts. Is it wet? So this property is useful for for studying things locally, let me give you an example. So let's take S any base schemes, and I suppose you consider a point in the scheme S corresponding to some residue field. So this is, you can write this as a map. Yes, but
There is a strange character like this, just before M.
yeah.
Before
Ah,
okay.
such that, sorry.
Yes,
Okay. So if you take a point in a base scheme S, so you look at the canonical map of a residue field inside the scheme S, it can be factorized into a closed immersion, say YIX, and a pro-open immersion. So this map is just a projective limit of open immersions, and then you can define, so this follows BBD, you can define X upper star to be, well, actually this is just, this is not a definition, this is just true, X upper star, but you can also define X upper shriek. Note that X is not a finite type, but you can define something, and this will just be IX upper shriek, JX upper star. Okay, so this is a definition and this is a fact. Then the lemma, if you want, is that if T is continuous, then the family of functor functors X upper star for X in S, respectively X upper shriek for X in S, is conservative. So this is obviously quite interesting because you can reduce, suppose you have a map in T of S, so this functors goes from T of S to T of X of residue field. Suppose you have a map in T of S, to show that it's an isomorphism, you can just restrict to residue fields, and so you restrict to a case of fields. But of course, to do that, sometimes you have to show that some functors can be exchanged and so on. But maybe I have an application of this. There are plenty of applications, but this is due to Ancona, Hubert, Annette Huber, and Simon Pépin Le Haller. And it tells you that for any scheme S and any algebraic group scheme G of S or S, the motive of S in G, this times considered in the general category of motives with Q coefficients, or S, admits a Chaucunet decomposition, a so-called Chaucunet decomposition, which means here that there is a canonical isomorphism between the motive of the connected component of G or S plus some factor, which is a sum. So it goes from 0 to some integers that they denote KD of G of S. And this is a symmetric object with respect to a tensor product of some motive, which is in some sense M1 G of S. One motive is associated with a group scheme, okay?
So in this set S, do you allow non-closed points also.
What?
So this X may be non-closed point also.
Yeah, sure. It's and you have to consider all these points. And this is where, so you can see that the continuity property will happen here. Okay, so the proof goes like that. So you first construct an object here, like that here, and you construct a canonical map from this motif to this one here. And then to show it's an isomorphism, you use this theorem to restrict to a case of field, or it was proved before by.
The sum runs from n equals 0 up to
Some integer, so maybe and 0 to some integer k, and k is denoted by as kd of g of s. I'm not sure it means Kodaira dimension. Okay. What?
What was about this distribution? It was an arbitrary or
I think it's arbitrary, yeah. Arbitrary algebraic group scheme. So in case it's an abelian variety, then you will recover a theorem of Moore and Denninger, more or less, for Choquenet, for if you replace if you use Chow motives here, and you are over field. And it's the usual decomposition of a cohomology of an abelian variety, but they extend this to any algebraic group scheme, which is nice. Okay, the proof is also an easy exercise using the localization triangle, so and the continuity property to show that you can manage this property. So you start by looking at the generic point, and okay, I let you go. Yeah.
This algebraic group scheme will not be even flat over S.
What?
This group scheme will not be even flat over S, I think.
This one here, yeah, I think it's not flat in general. Or
suppose it's just, let's say,
is it?
it is a group scheme over both points of S, and that's it.
Yeah.
Yeah, so here this really mean, so maybe I should, so in particular it's not étal, and if P is any map from X to S which is, say, separated of finite type, we also define MS of X as P lower shriek, P upper shriek of a constant object, so that this may explain why this can be defined. I think, yeah. Okay. Okay, next, so this is a first tool which might be useful. These are all wet. The second tool, which is fundamental in these questions of finiteness, is the so-called absolute purity property, something that we have already seen in one talk. try to write. Second is so-called absolute purity. So let me recall something we have seen that already in the talk of Maria Eckerson, that we can define, even in this abstract context, fundamental classes. So I need some notation to do that. So in this abstract context of any motivic triangulated category, if I have, say, F from X to S, any separated morphism separated of finite type, and if I consider V a virtual vector bundle, so in the category K of X, say, and an integer n in Z, I can define the bivariant theory of X over S. Maybe I'll denote this like that: H and V with coefficient in T as a group of morphisms in T of S from F lower shriek of the Thom space of X of V over X shifted n times, and with coefficient in just the constant object. Okay, so the only remark is that the stability property implies that for any say any vector bundles over X, I should write this, the Thom motives of E is tensor invertible. So this is over X. Maybe I should have denoted mx Thom of V, and using also some coherence property of the fact of this object here, you can extend this functor m Thom to the category of virtual vector bundle, which are in some sense formal difference of vector bundle. Okay, and there's a theorem, relatively recent theorem due to so myself, Ancona, Jean, and Adil Khan, which says that even in this abstract case, for any map F from X to S, which is, so we need quasi-projective, and L local complete intersections. So here it means that it can be factored globally as a closed immersion into and followed by a smooth morphism. Then in this case we got a canonical fundamental class of S which belong to H0. We have to put the virtual tangent bundle of F, T of F, with coefficient in X of S and T. So I'm satisfying good property. I'm not. The main ones are stability by transversal base change and compatibility with composition in a suitable sense. And there is also a uniqueness statement that I don't want to do, but plus uniquely determined by some of these good property.
The second subscript is tau.
Yeah. So let me write concretely what it means. So actually, the map eta f so is a map like that from f lowerstring of a motif of some Thom space to 1, and I will write it by adjunction as a map from the Thom space over X of a tangent bundle, and it goes to f upper shriek of 1s, a constant object. Okay, so it's funny to recall now the isomorphism that I wrote for coherent sheaves at the very beginning of my talk, which was a computation of this object in some under some additional other assumptions in the category of coherent, in the derived category of coherent sheaves. And so this, in some sense, justify our, I think it's the third definition. We will say under this assumption that T is F pure for a morphism F quasi-projective LCI if the map eta F is an isomorphism. And we will say that T is absolutely pure if for any fx to s which is quasi-projective and such that x and s are regular, we have eta f, we have T is F pure. I just recall that the morphism F from X to S is in our base category of base scheme S. Okay. So this property of absolute purity was advertised by Grothendieck in SGA5, and already it was clear that for him it was the condition that allows to formulate duality. So that's what will happen afterwards. Let me give you some example, waiting for this big application. So actually this property happens frequently because of the following example. If T is continuous and say Z1, or I should maybe, sorry. And if you assume that S is a category of K-schemes, in the theory and finite dimensional is not really useful, but and that T is in that T is Z1 over P linear if the characteristic of K is equal to P is strictly positive, then in this case T is absolutely pure. Okay. The fact is that because of the six-functor formalisms, this eta F will always be an isomorphism if F is smooth, for example. And also, it will be an isomorphism easily if F is any quasi-projective morphism between smooth schemes over some base. Okay. And now to deduce the case of arbitrary regular schemes over some K is perfect, sorry. And you use Popescu's theorem, which will say that any regular K-schemes, say, of finite type is a projective limit of smooth K-schemes. Okay. What?
At what point do you need the annual
Now that I think of it, I think we don't need, but no, you need that because if you take an inseparable extension, finite experience, inseparable extension of K that does not exist, well, take K of T and you take an infinite, an inseparable extension of K of T, then this scheme is regular. The spectrum of this scheme is regular, but you cannot use Popescu argument for this, or can you? Okay, so I put that to be sure, but I'm not sure this is really needed in fact. Okay. For duality, you will need these kinds of assumption anyway, but also because it was introduced. Okay, you can also formulate the absolute purity property for an object of T, or say an object of SH. I will let that, and and the fact that it is that you can obtain other example of absolutely pure objects of a stable homotopy category. For example, you can consider this absolute purity property in the category of module of KGL module, for example. And then a basic fact is that you can prove that KGL satisfies the absolute purity property. This is because of Quillen's results, especially localization fact in K-prime theory, and the fact that K-prime is isomorphic to K if you restrict to regular schemes. And so this gives you another example of absolute purity, which in the next talk will apply to rational motives. Another example that is not written, but that should be written, and that appeared in the talk on Wednesday by previously, is the case of Hermitian K theory, which should work as for KGL theory because of a result of Markov-Schlichting. So I think. So we have several examples of this absolute purity property. Let me say also that for étale sheaves, torsion étale sheaves, it was first proved by Thomasson for certain torsion group using K theory, and then it was generalized. So the proof of Thomasson actually applied to to the category of L-adic étale complexes. So it proved absolute purity for this category, and then Gaber generalized the method and proved it in general for any torsion category of étale sheaves. Okay, but now I want to go to the application of these tools to the constructible objects. broken is what about the so-called Grothendieck-Verdier duality. And because of lack of time, I will write you a big theorem in order to make several statements in one. So this theorem is due to many mathematicians. The method, the basic method is essentially, well, due to the method of SGA4, the method of Gabor. Then it was translated into this framework by Ayub first, then slightly generalized by Szysinski and myself for the rational case, and again slightly extended by Darko and myself. But the methods are basically that of SGA4. So we need assumptions in order to get these results, and these assumptions are essentially resolution of singularities. So we need assume one of the following cases. First, we assume that T is continuous, S is the category of K-schemes for K perfect. Again, K-schemes Noetherian finite dimensional, but they need not be finite type. Maybe I will write essentially of finite type. And again, if the characteristic of K is positive, strictly positive, then we require that T is Z1 over P linear. Okay, so the resolution of singularities that we want to use here is, of course, the Young results. The second possible case is you assume that S this time is the category of S0 schemes, which are again essentially of finite type. Finite type, where S0 is an excellent Noetherian scheme of dimension less than 3. This is to use Gabor version of resolution of singularity without a base field. And then you also assume that T is Q linear, satisfies absolute purity, so pure, and I will say here it is oriented because okay, so remark that under this condition we know that T also satisfies absolute purity, so this is always an important argument. Then in this case we have 3 properties. Then first of all, a category of constructible object is generated by, say, primitives of a form so this is F low star of a constant object with N, where F from X to S is proper, X is regular, and N is an integer. So instead of having the motive of a smooth object here, we have this object here, which is something like a motive with compact support in some sense. But here we just require that X is regular and the morphism is proper. So this is the first part, good generators for the category for constructible object. Then second thing is that TC of S is stable under 6 operations. So F lower star and then P upper shriek and internal for morphism, for F lower star if F is of finite type. You still need this assumption here. Otherwise it won't be true for obvious reasons. And the last thing is that for any morphism separated again of finite type, such that S is regular, the object dx equal to F upper shriek on S is dualizing. This means that if you put the curly dx is the functor internal with coefficient dx, the canonical map, from the identity to d square is an equivalence, an isomorphism. In other words, d of x is a contravariant autoequivalence of TC of x is an equivalence on, is dualizing in T of C of S. So this is an isomorphism on constructible motifs. Okay, so it means that any constructible motif admits a weak dual. This object is in some terminology. Okay, so that this is what I referred before. This is what people call the Grothendieck-Verdier duality, because this was of course discovered by Verdier and after Grothendieck. Okay, so maybe I can give you some. Yeah.
So in the first line is generated by.
Yeah.
Is generated by
three motifs of a form Kenwright object, if you prefer. So it means that this TC of S is the category which is obtained through this object by taking extension or direct factors, but not infinite sums, of course.
3x is not regular.
What?
3x is not regular.
Here?
3.
X is not regular, yeah, of course. S is regular, but not X. So you see, because of the absolute purity property, if X was regular, here we will have some Thom space. Thom space are invertible, so this will be the dualizing object. But if X is singular, this is more complicated here, and it's exactly what the analog of what Grothendieck obtained for covariant sheaves. Yeah. So. Maybe just well, maybe I'll just say it because it's I have not much time. So the first point is really a critical point, but it's obtained by Desvisage, and you have to use resolution of singularity to get these two properties together, proper and regular. If you consider only one property generated by these but f proper, or generated by these but x regular, then this is easy. to get the two property in the same time, you really need to do something and actually use resolution of singularities. So this property here, so in case A, this is essentially the method of SGA4 using de Jong. In case B, it's more subtle, but the proof is more or less, it's not exactly the same, but it's the same thing than the proof of Gaber of the analogous fact for the étale shift, for the category of torsion étale shifts, which has appeared in this Asterisk book very recently. And this part here, I have not time to do it, but actually it's once you have these two properties, this is formal. It really just follows from this part here and this one. And of course, this one, the second part here, is obtained to prove that this object is constructible in general. This is the only part where it's used. Then it's just a play of the six-functor formalism and this fact here. Okay. So the examples where this can be applied are given by, so you can take, for example, SH and invert P and restrict over fields and over K-schemes and invert the characteristic, the exponential characteristic. And it works also for, we will see in a minute, for the category of rational motives because of this property here. So also this, the first property is really important, and for example it was used by Michael Bondarco and David Deber to get the proper weight structure on the category of rational motives.
Okay. So certain Chow motives if you these motives in part 1 are certain reasonable realizations of Chow motives to the relative setting.
Yeah.
If you take them in game and shift them a little by 2n.
Yeah, you can ask Michael for more details about this weight structure. Okay, I think I will stop that otherwise.
Any questions or comments?
So I have two questions. So first is I can see, so this S is the S0 scheme, right?
What?
S0 scheme in first.
Here?
S.
Yes, it's an excellent Noetherian scheme.
And this S is over S0, right? S0.
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 S0?
Yeah, F from X to S, right?
This all schemes which appear here are schemes in this category here. So X and S are essentially a finite type over this.
So S may not be of dimension less than equal to 3, right?
S may not be?
Of dimension less equal to 3. So I didn't see where we use resolution of similarity of S0. Can you say a little bit where the fact that S0 has dimension less than equal to 3 is used here in the proof of 1?
So it is used, so so you have a scheme X, usually you have a scheme X and a closed subscheme inside, and you want to find a blow-up such that the blow-up is regular and the complement is a divisor with normal crossing. And to get that, you will not get that in the case B, you will just get an alteration. And to get this alteration, this is where you need this assumption. Actually, you need that, in Gaber's theorem, you need that the category of schemes are of finite type over S0. But then you can extend by this continuity argument to, then you can extend to essentially, maybe I missed, maybe I need continuity here. Just to be, no, I'm not, no, I don't think so. Okay, so this is for this theorem of Gaber, existence of alteration, which not only give you a regular schemes, but also complementary divisor with normal crossing. It's used maybe not here, but here in the proof of Gaber. So to get this first property, you need a weaker resolution of singularity at the full Gaber result. But here you definitely need this thing about the divisors. And so yeah, this assumption that S0 is of dimension less than 3 X-Newtonian, I don't know exactly why this happens, but it's in the work of, I think, Gaber and maybe Tamarkin. So I cannot give you details about this. Of course, for application, this is more than sufficient, I guess, I think.
My second question is, where did you use K is perfect?
What?
Where do you use the K is perfect?
If I remember correctly, this was for applying Popescu's theorem. But you see, there's no finiteness assumption here. So you can, in the application, you can, well, this is essentially a finite type, but yeah. You can take K is FP or Q, it will be sufficient in practice. So this is why we don't really care about. Yeah.
What was Mikhail's comments about the Chow motif in the line 1?
These objects, so if you don't twist, I think these objects are motifs of weight 0, right?
Yes.
If you don't twist. So, and motifs of weight 0 are the analog of Chow motifs. For example, it's known that if you are in case A, what is it? You look at the subcategory generated by.
You can consider generalization is of weight 0 in the sense of BBT, and also you can yes, you can compute the category.
Yeah, of Chow motifs. So that's what.
Chow motifs in terms of certain algebraic cycles. This was done by
Corti, Hanamura, and Jin. Corti and Hanamura had defined Chow motifs for schemes over a field. And then Jin showed that if you look at these kinds of objects, say, or more precisely motifs of weight 0, then the category is equivalent to the category of Corti and Hanamura. So you really get back to classical, say, Chow motifs.
And you should get Chow motifs if you're over field.
Yeah. Sorry. Yeah, of course. If S is a field, this is.
That's fine for the